So let's recap. We're on a quest for public key encryption schemes. We reduced that to finding key encapsulation mechanisms, a somewhat simpler type of cryptographic object. And then we gave several constructions of these key encapsulation mechanisms. What we turn to now is justifying those, which means giving security proofs for them. Now, any security proof relies on some assumptions on the base primitives or ingredients used by the schemes. In this case, for the KEMs that we gave, some of the primitives are ones on which the assumptions are quite natural. For example, we gave KEMs based on the computational Diffie-Hellman problem, so we would be assuming that problem is hard. Or the ones based on RSA, that the RSA function is one way. But they also used hash functions. And the question is, what assumptions are we going to make on them? And that's not so easy to answer. And the approach we're going to take is to model them as ideal or random and capture that formally in what's called the random oracle model. So in the random oracle model, all entities or parties have access to an oracle that implements a random function. In our case, what that means is that each of these functions, h sub I, is defined by a game procedure, and that game procedure implements a random function in the usual way. When you give it an input x, it checks a hash table, and if position x is currently undefined, it fills it with a random value chosen from the correct range. And if it was already defined, no change is made and that value stays stable. And that value is returned as the result of this function applied to x. This table is maintained by the game and assumed to be initially bought at all entries. And the inclusion of I here makes sure that the tables are effectively distinct for each different function. So when we say that this procedure is added to the game, we refer to the games which define security, the INDCPA, INDCCA games for the different primitives. And this procedure, once in these games, can be called by scheme algorithms. So scheme algorithms are now refer to or take this procedure as an oracle, and the games execute these algorithms. For example, in the KEM game, the enc procedure executes the encryption algorithm of the KEM, and that algorithm will now use this as a hash function. Game procedures might themselves call this, if they like, independently of scheme algorithms doing so, although we haven't particularly seen that happen yet. Most importantly, this procedure is available to the adversary, and this reflects that it's a public function, and the adversary can provide an X of its choice and get back the value. Now, in this model, we are going to claim that our different key encapsulation methods are, in fact, secure. So let's see how that works out for the first one that we gave. So this was the ChemCDH construction and the CPA version of it. And we're claiming that indeed it is INDCPA secure in the ROM. The assumption for that is that the computational Diffie-Hellman problem is hard, and rather than have some assumption on the hash function, we will work in the random oracle model so that the hash function is in fact a random function. Remember, INDCPA here refers to the definition for key encapsulation mechanisms. So here's a full and quantitative statement of the theorem. We fix a cyclic group. The group, its generator, and its order are public. And we consider the key encapsulation mechanism, that is the ChemCDHPA one, as described earlier. It has a key length k, which is the output length of the hash function, and here the random oracle. Now we consider an adversary, and I'll assume it makes just one query to the enc oracle for simplicity. We saw earlier that making more queries doesn't help beyond increasing advantage linearly by the number of queries. So that simplification is without loss of qualitative security, at least. Now, at this point, the hash function itself is also a game procedure. So the way we measure the resource usage there is also by queries. So we're going to assume some number of queries are made by the adversary to the random oracle hash function. Now the theorem says that there is a computational Diffie-Hellman adversary B such that the following holds. If you consider the advantage of our given adversary A in violating IND-CPA security of the KEM, it's at most Q times the advantage of B in violating the hardness of the computational Diffie-Hellman problem over the group G and generator G. And as usual, the running time of B is about the same as that of A. So given that we will work in groups where this is very small, this justifies with proof the security of the ChemCDHPA KEM. So let's turn towards justifying this claim, and we'll start with stepping aside and generalizing the CDH problem a little, because that will be a convenient tool in this proof. So we'll fix, as before, our cyclic group, and we'll consider an adversary B prime. It's trying to solve the computational Diffie-Hellman problem, but unlike the usual adversary, who gets one try at guessing the key value, this one has multiple tries. So let's see what that means. We write the game with the same notation. The initialized procedure, as in the CDH game, picks two random exponents and returns the corresponding group elements G to the X, G to the Y. Finalize, in our original CDH problem, took one group element as input, but now it takes Q of them, where Q is some parameter associated to B prime. They are all guesses as to the value of G to the power XY. And if any of them succeed, then we set the flag win to true, and eventually that's what the game returns. So in other words, our adversary is given a bunch of chances to win, and if one of its guesses is correct, then it will indeed win. Again, the usual CDH just corresponds to the special case that Q equals 1. So the CDH advantage of our adversary is just the probability that it wins when it plays this game. Now, this isn't a qualitatively different problem. What this lemma says is that if you have an adversary of the form we just described with Q outputs or guesses as to the CDH solution, that we can design an adversary making just one such guess, meaning having one output in our conventional type, and the advantage of our Q output adversary is at most Q times the advantage of the single output adversary. In other words, if I assume hardness of CDH against adversaries with Q outputs, it's not qualitatively a new assumption because I can relate it to my original one via this formula. The proof has to give a design of B and elucidates that it's really quite simple. All that you have to do to design B is that B will simply pick at random one of the Q outputs that B prime returns and use that as the single guess that it's allowed. So B also gets input G to the X, G to the Y. It needs to find G to the power XY, and it has only one shot at doing so. It asks B prime, what do you think are the value, your guesses as to the value of G to the XY? And B prime says, I think it's one of these Q things. And B says, I'm going to pick one of them at random and return it. And it's not hard to see that with 1 over q chance, it hits the one that makes B prime win, which justifies this. With that in hand, let's return to the proof of the theorem that claimed IND-CPA of the ChemCDHPA chem. We've been handed an adversary A, and our goal is to assess our upper bound disadvantage. To start, let's recall two things, a little bit about the definition and also about the scheme, which here have to be intermingled. So in the definition, our adversary is given the public key first. That here is g to the x, where x is some random point in Zm according to our scheme. It's allowed access to the enc oracle, but it makes only one query. That query returns a ciphertext, and that ciphertext in our scheme has the form g to the y for some random exponent y. Additionally, the adversary gets from that same enc query a challenge key. What does that mean? The game had picked a challenge bit at random and then set k0 to a random k-bit key, while k1 was the correct key corresponding to the ciphertext g to the y. In other words, it was obtained by hashing this over here, where this here is the Diffie-Hellman key corresponding to g to the x and g to the y. And the k the adversary gets was either k0 or k1. And the adversary's job is to determine this challenge bit b. Most importantly, it has oracle access to the hash function, because here we are in the random oracle model, and the way this hash function is computed is through that interface. Now, one sees here a strategy that allows A to succeed in its task of determining the challenge bit. How would that work? It takes the quantity g to the y, g to the xy, and queries that to its random oracle h. And lets k prime be the response. So it makes the query that corresponds to the derivation of k1. Well, if the challenge key k it got was actually k1, then k prime and k would match up, and so it could say it did return 1. If k prime is not equal to k, then it's more than likely that k was actually k0, and so it can return 0. And so this strategy effectively works. So why are we nonetheless saying that our adversary has a hard time figuring out the challenge bit and the scheme is actually secure? Well, the reason is simply that if it could make this query, it could indeed win, but it doesn't have an easy way to do that because it doesn't know how to compute g to the power xy from what it's given over here. And so it will find it hard to actually make the query. Let's take that a little further with regard to doing the proof and building the required adversaries for the reduction. So consider two cases. One is that A does not make this crucial query to its random oracle. Our claim is that in that case, it has zero advantage. It has no ability to tell better than a random guess whether the challenge key k it was given was actually equal to h on those inputs or just random. And that's by the nature of a random oracle, where as long as a query hasn't been made, the output is in fact random from the point of view of the adversary. On the other hand, suppose A does make the query, then we will use that as a way to solve the computational Diffie-Hellman problem. So we now proceed to formalize all that using some games. So we're going to write a pair of games G0 and G1 with the following properties. We're going to be looking at the right-left formulation of chem IND-CPA security. So we know that the IND-CPA advantage of A is the probability of returning 1 in right minus in left. We're going to write our game so that the right game is captured by G1 so that this holds, and the left game by G0 so that this holds over here. Once we've done that, the advantage of A becomes this difference. But the games we write will have an additional property. They're going to be identical until bad. Remember, this means that they differ only in code following the setting of the bad flag to true. As a result, the fundamental lemma of game playing tells us that this difference is bounded by the probability that one of them, whichever one we want, I'll pick G0, sets the bad flag, meaning that bad becomes true in the execution of G0 with A. And that will reduce our task to bounding the probability that bad is true. All right, so that's where we're headed, but how do we actually write games that make that happen? Well, there is some cleverness involved in that. Often in game playing proofs, some creativity is exercised right at the start to formulate games in a convenient way that does take some elucidating at the beginning. So again, we are looking to reflect the right and left games, the left game in G0, the right in G1. Initialize will pick the secret key little x at random, create the public key, and provide that to the adversary. It'll also pick the ciphertext. So the ciphertext has the form g to the y, where y is a random exponent. Since there's only one enquery, we may as well make that choice in initialize, and then we can stick the ciphertext here as a reply to the enquery. The other component that the adversary gets in the enquery is the challenge key k. That's supposed to be a random string in G0 and the correct key, the hash of g to the y and g to the xy in G1. However, our game simply picks a random string and puts it here. Now at first that seems fine for G0, which is the left game, but not G1. But actually we can't say that yet. What we're going to do is set up the replies to the random oracle procedure in such a way that this becomes fine also in G1. How do we do that? Well, when a query is made by the adversary to this random oracle, it begins by populating the corresponding hash table with a random value. Think of that as optimistically saying, most probably this is what I want to return. Now here we have a little simplification. One should not do this if that query had already been made and a value assigned. But that's addressed here by simply assuming that our adversary never repeats H queries, which is without loss of generality, because we can always modify an adversary to make sure that happens. So we'll proceed under that assumption. Now we can parse this query as some y and some z, which are the two group elements, which are kind of expected to have a form kind of like this. So now, suppose that this y matches up with the g to the y here, while z is indeed the correct Diffie-Hellman key for that g to the y. If so, in game G1, we say, now, wait a minute, that means that the reply to the hash query should be this, because that's what I ought to be returning here. So I now say, never mind my choice here, I'm going to rewrite it and actually stick k into the hash table for w, meaning define the value of the hash function on this particular w given by this z and y to be the same thing I already put here, and eventually return it. So additionally, we flag this event as bad. Why is it bad? Because we expect it to seldom happen because it involves the adversary figuring out this. So now let's go back to our two claims over here. The easy one is the left game. In the left game, the box code is absent. So all the replies to H queries are random, and this is a random independent string, and that's how things should be in the left game. In the right game, this is indeed equal to H applied to Y and Z because of this box code. And so again, this statement will be true. So now perhaps a question that might arise is, how is this game computing g to the power xy? Well, it's easy enough for the game. It knows both x and y. And it's fine for games to do operations like that. We have to make sure, however, that we can still build our adversaries to compute this even given only g to the x and g to the y. So now we already went through this aspect. So we're down to saying that we need to bound the probability that G0 sets bad. And we'll do that by writing an adversary against the CDH problem, exploiting our prior generalization. We will make this a Q output adversary. Remember, Q is the number of queries to the random oracle made by A. And the probability that G0 sets bad will be bounded by the CDH advantage of our Q output adversary B prime. Finally, we can use our lemma to turn that Q output adversary into a regular 1 output 1 and incur a factor of Q, and that is what will give us the theorem statement. So let's look at how we build our B prime. Its inputs are some points g to the x, g to the y. Of course, it doesn't know little x and little y, it just has the group elements. And its job is to compute g to the power the product of x and y. How does it do that? It's going to run A. It first has to give A a public key, for which it uses one of its inputs. And next has to simulate the encryption and hash oracles that A desires. It's going to do this by mimicking game G0. In game G0, the reply to the encryption oracle was a random string k and g to the y. So it does the same, puts g to the y here, and itself picks this random string k to put here. In game G0, replies to the H queries are very simple. They're just random strings. So it just does the same thing. It populates the table with a random value and returns it. Additionally, however, it keeps track of all the Z parts of these queries, the second part over here. Why is that? Because it knows that somewhere in one of these queries, that is going to be g to the power xy. This will be g to the y, this will be g to the xy, and that's what it's seeking. However, it doesn't really know a priori in which of those Q queries that'll happen. And the way it gets around that is that it just collects all the candidates and outputs that list. And as long as game G0 returns 1, this list will contain somewhere in it that correct g to the xy value. And that's enough to make B prime win. So this proof and the games and so forth do need some work going over to understand the different steps and subtleties and so forth. Now, these types of schemes based on the Diffie-Hellman problem are present in practice. DHIES, the Diffie-Hellman integrated encryption scheme, and elliptic curve integrated encryption scheme are some examples. The latter uses an elliptic curve group, which improves performance and reduces ciphertext size. And versions of these schemes are standardized in various places. Now, when we studied number theory, we had two main sources of hard computational problems for cryptography. One was the discrete log family of things from which we've already built a KEM, and the other was RSA. So now we're returning to the RSA KEM we gave, the CPA case, and we're going to discuss its security. So the claim is analogous to the one for the Diffie-Hellman case. We start by fixing an RSA generator. It's relative to that the particular key encapsulation mechanism we defined is constructed, and that's the KEM RSA CPA KEM associated to this generator. We let K be the key length, which is going to be the output length of the random oracle hash function. Now we take an adversary A attacking the IND-CPA security of the KEM. And we'll assume it makes only one query to the enc oracle, which as usual is without loss of generality by our prior results, and some number Q of queries to the random oracle. Since that's now an oracle, that's how complexity is measured. We will bound the success of A in violating IND-CPA security of the KEM via the success of an adversary I we construct in violating the one-wayness of the RSA generator. And this adversary, as usual, is about as efficient as A, although there is an overhead related to the number of RO queries over here. So we won't prove this in full, but the intuition is quite similar to the prior time, so let's at least try to give that. So again, we are looking at this adversary A running in the KEM game for IND-CPA security. And so it'll get as input the public key, which here is the modulus and encryption exponent, since we are looking at RSA, a ciphertext Y. How was that created? By picking a random point in Zn star and applying the RSA function to raise it to the eth power. Along with that ciphertext, which results from the single enc query A is allowed, is the challenge key. Again, the challenge key, depending on the challenge bit chosen by our game, is either a random string, K0, or the random oracle hash function applied to this Y over here. And K is whichever of those two the challenge bit indicates. And again, the adversary has oracle access to the hash function H. Now, in its task of determining the challenge bit, we again observe there is a simple way to do that. You just have to query little y to the random oracle, and you will get back this value. If that matches up with K, then it's more than likely that K was K1 and the challenge bit is a 1. Otherwise, more than likely it was a 0. The difficulty for the adversary is finding this value little y, because all it has is its encryption under RSA, and reversing RSA to go back to the original little y is hard. That would violate one-wayness. On the other hand, if the adversary fails to invert RSA at this big Y, it will have no advantage in determining the challenge bit, because without this query, it has no way to know whether it's looking at the hash of little y or a random string. And we'll leave anyone who's interested to reconstruct a full proof. Now, so far we've discussed the CPA security of KEMs. So we have given, remember, 2 KEMs based on Diffie-Hellman type problems, 2 on RSA, in each case 1 for CPA, 1 for CCA. So let's turn now to the CCA versions. They both work in the sense that the ChemCDHPA KEM we gave is IND-CPA secure. This again continues to be in the random oracle model, so both the hash functions, remember this one uses 2, are modeled as independent random oracles. However, while the CPA version depended on the assumption that the computational Diffie-Hellman problem was hard in the group, this needs stronger algebraic assumptions, namely what's called the strong Diffie-Hellman problem, or closely related the gap CDH problem. These problems ask that computational Diffie-Hellman remains hard even if your adversary attacking it has an oracle for the decision Diffie-Hellman problem, meaning it can go to the oracle with 2 things of the form g to the a, g to the b, and a guess as to g to the ab, and the oracle will tell it whether it's right or not. In the RSA case, again, we have our KEM RSA for the CCA case with its 2 now random oracle hash functions, and that is IND-CCA, and the assumption is the same as before, the one-wayness of the RSA generator. When we use the RSA KEMs to do public key encryption, we will, as per our paradigm, do that with hybrid encryption. So suppose you have a message M of some number of bits, say 500 bits to encrypt. Under the hybrid encryption paradigm, your ciphertext will consist of 1 point in the RSA group Zn star and a symmetric encryption of the message, which at best is 500 bits. And so you will have a ciphertext that's longer than an RSA group element by 500 bits. All right. Why go through all that? Because sometimes that overhead is undesirable, and OAEP is a scheme. Here it's directly for public key encryption, it's not a KEM, which encapsulates the message inside the group element in such a way that as long as messages are not too long, your ciphertext remains a single group element. It's illustrated here for the special case that the modulus has binary length 1024. Remember, the encryption key with RSA is the modulus and encryption exponent. Decryption key is the modulus and decryption exponent. It will use two hash functions, again modeled as random oracles. Here they're called G and H. And the first one is expanding, taking 128 bits to 894, and the second compressing, taking 894 back to 128. How do we encrypt? We are given a message M whose length is assumed to not be too big. It's somewhat short of the modulus length. And we have the public key and our two random oracles. There is, of course, some randomization. You can't achieve IND or CP or CCA security without it. So here we pick a random 128-bit string, and then we define an integer which we will use for padding. And it's effectively how much short of the maximum length is our actual message. Now take the 128-bit seed from here and concatenate it with this string, which is a bunch of zeros followed by the message, followed by some padding, enough to bring the length of everything to 894. And now we're going to do 2 rounds of Feistel. Remember, Feistel was the construction inside the DES block cipher. So what it does then is it runs R through G, adds that to this entire object over here to get T. But it also runs that through H and adds it back to R to get S. The merit of this structure is, on the one hand, to kind of mix up all of this so that ST is kind of random looking, but also in a way that's reversible. Anyone having ST can go back to R in this. Now, if we look at the string ST, it has length around 1024, and we treat it as an integer and apply RSA to it. So we raise it to the eth power mod n. Now note that all the security is effectively coming from here, because this part was all invertible. Nothing had happened there cryptographically yet. So, and that ciphertext is returned. Okay, how do we decrypt that? The decryptor has the decryption key little d. So first it reverses RSA and it gets back what should be this X over here. It parses that into 128 bits and the rest. Now it reverses the structure here, and since it's Feistel, it can do that. If you push T through H and add it to S, you get back R, and then as here you can push R through G, add it to this and get back something here. What it gets here, it parses. It just lets A be the first 128 bits, then it seeks the first 1 from the left, and everything to the left of that before A, it views as the message. It doesn't directly return the message. It first checks that this really is the string of all zeros. And if so, it returns the message, else not. This check is to limit the power of chosen ciphertext attacks and ensure chosen ciphertext attack security. So this works if you assume the underlying RSA generator is one-way secure. Then in the random oracle model for the two hash functions G and H, it achieves both IND CPA and IND CCA security. And due to that and its efficiency, it's been fairly popular. So there are various protocols out there that use it. For example, early versions of SSL and TLS, some versions of the SSH protocol, and different standards. PKCS #1 is the main standard put out by RSA Corporation for public key cryptography, and it percolates into many other standards from there. All right, so now let's consider in a more philosophical type of vein this random oracle model that we've used. The random oracle model is widely employed in cryptography to justify and prove security of practical constructions. And that's done through what's often called the random oracle paradigm, which means that we design and analyze schemes in this abstract model of the random oracle, which is effectively a thought experiment in which a random function is available as a procedure you can call. But in an implementation, we have no such procedure sitting in the sky that you can just call to get random numbers, and we have to instantiate the hash function. And we do that by replacing the random oracle with functions of the type we've described earlier, built from cryptographic hash functions like SHA-256 or shake. Now, once we've done this, the instantiated scheme is not the same as the abstract one. And so one should ask, what confidence or evidence do we have about the security of the actual implemented scheme? Asking that could also be phrased as asking, what properties should these actual hash functions satisfy so that they mimic random oracles sufficiently well to make this work? Well, that brings to mind PRFs, because PRFs are things that mimic random oracles effectively through the definition of a PRF as saying the adversary is unable to distinguish between a random function and the output of the PRF. But there's an important distinction. In those cases, security relied on a secret key that was embedded in the game and which the adversary didn't know. And when we use PRFs in any applications, we have to be sure we can supply it with a secret key and that the adversary doesn't have that key. But that isn't something possible in our current application setting. In public key encryption, anybody has to be able to encrypt without any secrets. And so we can't have encryption depend on some secret key. And that's what random oracles provide, is random functions in the absence of such keys. So PRFs are not the answer. So we could go back to the broadest question is the instantiated scheme actually secure, and what evidence do we have that that's the case? And the fact is that there is no proof that the actual instantiated scheme is secure based on what one might call a standard assumption about the hash function. What does standard mean? Roughly that it's given through a game in the style that we've discussed. However, in practice, this paradigm seems to work. Instantiations of at least natural cryptographic schemes obtained in this way with good hash function based implementations of the random oracle in fact have resisted attack and seem to be secure. But nonetheless, there is a gap here that's good to understand a little better. The random oracle model is a model. It's not an assumption on the hash function. To say, let's assume SHA-256 is a random oracle, not only is incorrect, but more importantly, it doesn't make sense because we have no definition of what it means for a function to behave like a random oracle, at least no definition under which all the different applications of the random oracle model would be pushed through. And the gap isn't merely conjectural. It is actually possible to find schemes, for example, key encapsulation mechanisms, that you can prove secure in the random oracle model. But once you instantiate the random oracle with some specific hash function, even SHA-256 or anything like that, that instantiated scheme is actually insecure. There'll be an attack on it. Moreover, that'll be true no matter what choice you make of the instantiating function. However, if one looks at these counterexample schemes in the literature, they tend to be artificial, meaning they're somehow created and contrived ways to fail. And the way that's done, roughly, is that descriptions of the hash function used in the instantiation can be passed back to the scheme, and the scheme can recognize them by running the description and somehow start doing weird things when that happens. So our sense so far is that the random oracle paradigm works, meaning the instantiated schemes are secure if there is a proof in the ROM, as long as the schemes are kind of real and natural, not artificial in this way. But we don't have a formal definition of this phrase in quotes. So where does that leave us with the random oracle paradigm? It's a good way to get practical schemes and to justify natural practical schemes and give provable support for them. And it works well in practice. Schemes with proofs in the random oracle model tend to be adopted and do well with regard to resisting attack. Also, there is a certain class of attacks which are very common. When cryptanalysts attack something like a public key encryption scheme or a KEM, which has a hash function in it, they tend to not try to use and exploit the internals of the hash function. There seems to be no reason to think that the internals of the hash function interact in any cryptanalytically profitable way with the number theory of the scheme. So effectively, the bulk of attacks are in the random oracle model, and hence a proof in that model tells you that the types of attacks typically mounted will fail. So the bottom line with this is to use the random oracle model, but nonetheless to do that with some balance and care, where one understands limitations as well as strengths and understands what might go wrong. And it's also a nice thing to research to figure out more about this.